In the last tutorial, we got a high-level introduction to the strange and wonderful world of Julia GP GPU by learning how to use the CUDA.jl package. Today, we'll dive deeper into the CUDA package by learning two more ways to use it. 1. How to create your own low-level custom CUDA kernels. And 2. How to access the built-in CUDA libraries. Will these two additional options be better or worse than what we saw in the last tutorial? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
This tutorial is a continuation of the previous tutorial, so I'm assuming that you've watched the last episode and that you have CUDA installed on your computer. As a reminder, CUDA will only work with CUDA-compatible GPUs manufactured by NVIDIA. So I'm also assuming that you have access to a desktop or laptop computer with a GPU made by NVIDIA. Like last time, much of the code that I'm about to share with you is from the HPC NRW video. A link to their video is in the description below. With that said, let's jump back into the code. In VS Code, open up a new terminal window if it's not open already. Open up a new Julia session by hitting Alt-J, then Alt-O. Maximize the REPL panel. Enter the package manager by hitting the closing square bracket. Activate your tutorial directory. Add the benchmark tools package and the CUDA package. Type in status to check the version numbers. Exit the package manager by hitting backspace. Restore the REPL panel. In the Explorer panel, create a new file named kernel_library.jl. This is optional, but I'm going to dock my REPL panel next to my code. Let's start by loading our packages and defining our constants. These are the same constants that we used in the last tutorial. Also, let's assign variables with the benchmark times from the last tutorial. These are the times for my hardware, so your times will be different. If you don't remember your times from the last tutorial, you can use these times as placeholders. I've changed the variable name for the GPU time to broadcast time, since we will be benchmarking two additional GPU times in this tutorial. Here, broadcast refers to Julia's broadcast operator that we use to calculate Saxby. Okay, let's learn how to create our own custom CUDA kernel to calculate Saxby on the GPU. A CUDA kernel is just a function that runs on the GPU. Let's start by initializing the vectors x, y, and z as Cu arrays. Before we can create our CUDA kernel, we need to understand how CUDA organizes the tasks in order to execute them in parallel on the GPU. CUDA does this by grouping the individual tasks into threads, and then grouping those threads into blocks, and then grouping those blocks into a grid. Okay, let's go through this code. The variable nthreads is the maximum number of threads per block. For all recent NVIDIA GPUs, the maximum number of threads per block is 1024. Unless you have an older NVIDIA GPU, your value should also be 1024. The variable n blocks is the total number of blocks needed to perform all of the tasks. Since we have 100 million elements in each vector, the number of blocks is just 100 million divided by 1024, which is the number of threads per block. As a result, we get a total of 97,657 blocks in the grid. The CLD function is from Julia Bayes, and it's short for ceiling division, which just rounds up to the nearest integer. This isn't complicated math, but it can be confusing the first time you see it, so let's take a look at a visual. Since our dimension variable is equal to 100 million, that means that our task is to calculate Saxby 100 million times. Although our GPU is very powerful, it cannot handle 100 million tasks simultaneously, so these tasks need to be broken down into smaller batches. In order to do that, CUDA takes these 100 million tasks and groups them into 100 million threads. The 100 million threads are then grouped into blocks, which contains a maximum of 1024 threads per block. As a result, there are a total of 97,657 blocks. Finally, all 97,657 blocks are grouped into one grid. So this is how 100 million tasks are grouped into threads, blocks, and a grid. Now that we understand how CUDA is organizing the tasks, let's see how to create the actual CUDA kernel. As you can see, this looks just like any other Julia function definition, but the contents are unusual, so let's go through this code. The parameters are the variables for the Saxby calculation. As a reminder, Saxby stands for single precision a times x plus y. The first line of code is calculating the index number using the CUDA built-in functions block index, block dimension, and thread index. When CUDA organizes the tasks into threads, blocks, and a grid, it also assigns index numbers. Like C, CUDA uses zero-based numbering, so the first element is located at index 0 when you're using CUDA. But since Julia uses one-based numbering, the first element is located at index 1 when you're using CUDA.jl. In our example, the block index number goes from 1 to 97,657, since that's the total number of blocks in our grid. Our block dimension is 1, since we're using a vector, which is a one-dimensional array. The CUDA block dimension will either be 1 for a vector, 2 for a matrix, or 3 for a three-dimensional tensor. The thread index goes from 1 to 1024 in every block. So going back to our code, it starts with a block index number of 1, and then subtracts 1 from it, resulting in 0. In this example, the block dimension is always 1, so 0 times 1 is just 0. The thread index also starts at 1, so the first index number I is just 0 plus 1, or 1. Using this syntax will allow us to map all 100 index numbers in our vectors to the CUDA index numbers for blocks and threads. Next is the code for the actual Saxby calculation. Notice that we are not using a for loop, nor are we using a broadcast operator. Instead, we're using a conditional statement. This is the task that will be mapped to every thread in every block in the grid. The task mapped to a thread is independent of all other tasks, which is what allows it to run in parallel on the GPU. As long as this condition is true for that individual thread, then the Saxby calculation will be executed on that thread, regardless of what's happening in any of the other threads. The inbounds macro is from Julia base. Normally, Julia will check the range of an array in order to ensure that operations performed on it are within the range. Using the inbounds macro removes that automatic check, which will improve the performance. But that performance improvement comes at the price of removing a safety check, so it also comes with a warning that users are now responsible for performing that check manually. Okay, now that we've defined our CUDA kernel, we're ready to run it and record the time. Executing a CUDA kernel is called launching a kernel. We can launch a CUDA kernel by using the CUDA macro, while including the number of threads per block and the number of blocks per grid. So on my GPU, it took 2.796 milliseconds. Let's record this time. The time will be different for your GPU. Before we proceed, there's one thing that I want to point out that I didn't explain in the last tutorial. You don't normally need to use the CUDA sync macro, but you do need to use it whenever you use the btime macro to measure the time, or for any other situation when you want the CPU to wait for the GPU to complete performing its tasks. Okay, going back to our kernel. Since our kernel didn't return any values, let's just check to see if it performed the Saxby calculation correctly. Okay, so that looks good. All of the values are 4.1416, which is the correct value. Now, let's compare the performance of our CUDA kernel compared to the CPU, and compare it to Julia's broadcast operator on the GPU. So this custom CUDA kernel is about 19 times faster than performing Saxby on my CPU. The custom CUDA kernel is also slightly faster than Julia's built-in broadcast operator that ran on my GPU. It's not dramatically faster, but it is indeed a little faster. Pretty cool, right? So the takeaway here is that the CUDA kernel does take a little extra work to create, and does require an understanding of how CUDA organizes your tasks to run on the GPU, but that effort may result in better performance. Regarding performance, is it better to create your own CUDA kernels, or is it better to simply use the built-in CUDA libraries? Let's try using a CUDA library next to find out. CUDA comes included with these libraries that have been optimized to run on CUDA-compatible GPUs. For this example, we're going to use the CUDA cuBLAS library, which is the CUDA version of the basic linear algebra subprograms library. As an FYI, there is no documentation for the Julia wrappers for the functions in the cuBLAS library. NVIDIA does have documentation online for the cuBLAS functions, but the functions in the Julia wrapper are different. The Julia wrapper for the cuBLAS library contains a function called AXBYBANG that performs the Saxby calculation using the vector length, the constant a, the vector x, and the vector y as function arguments. Rather than using a vector z for the output, this function will overwrite the values in the vector y with the results. Just to check, let's take a look at the variable y. As you can see, it's a Ku array with 100 million elements, but the values are slightly off. Interestingly, using this built-in library is not as precise as using Julia's broadcast operator, or using a custom CUDA kernel. Let's reset the values for the vector y, and then try timing the kubelet function to see if it's faster or slower than the previous options. So on my GPU, it took 2.308 milliseconds. Let's record this time. But before we go on, there's something funny about the values contained in the vector y. Just like before, the variable y is a Ku array with 100 million elements. But this time, the values of the elements are completely off. I'm not sure what's causing this error. We know that the kubelet function works because we just used it, but for whatever reason, it doesn't work when trying to record the time. I think the actual time is correct, but seeing these results doesn't exactly inspire confidence. In any event, just to complete this process, let's compare the performance, assuming that this time is correct. So if this time is correct, calling a function from the kubelet library that runs on my GPU is about 23 times faster than calculating Saxby on my CPU. It's also roughly 1.3 times faster than using Julia's broadcast operator on my GPU, and roughly 1.2 times faster than launching a custom CUDA kernel on my GPU. If that's correct, then calling a function from the CUDA library is the fastest option. But it may come with some side effects. That's a lot to think about, so let's recap the 3 different ways that we use the CUDA.jl package to calculate Saxby on the GPU. And then, let's go through some of the pros and cons of each option. During our exploration of the CUDA.jl package, we learned that there are at least 3 different ways that we can use it. 1, we can use it just like any Julia package along with our Julia code for high-level, general-purpose programming. Or 2, we can write our own low-level custom CUDA kernels. Or 3, we can use the Julia wrappers for the built-in CUDA libraries. Some of the pros of using it just like any other Julia package is that it's simple and that it works well within the Julia package ecosystem. The main con of using it just like any other Julia package is that it may not give us the fastest performance since we're using high-level abstractions. When it comes to writing our own low-level custom CUDA kernels, some of the pros are that it gives us complete control over how our tasks are executed on our GPU, and it may give us better performance. Some of the cons of writing our own CUDA kernels is that it does require more work, and it does require an understanding of how CUDA organizes the tasks to run on the GPU. Finally, when it comes to using the Julia wrappers for the built-in CUDA libraries, some of the pros are that it's easy to use and that it should give us the optimal performance. But some of the cons of using the Julia wrappers for the built-in CUDA libraries are that the calculations are not very precise, and these libraries may not play nicely with other Julia packages. Also, there's no documentation for the Julia wrappers for these CUDA libraries. So there you have it, folks. 3 different ways to use the CUDA.jl package. each with its own pros and cons. Pretty cool, right? When you get a chance, don't forget to show your appreciation to the developers for creating a really awesome package and for sharing it with the Julia community by going to the GitHub page of CUDA.jl and giving them a star. Well, that does it for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, you can support me for free by smashing that like button, leaving a comment, sharing this video, and by subscribing to this channel. If you'd like to support me financially, you can make a one-time contribution by using the Super Thanks button. You need to be logged in to see the Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.